Okay, so we're going to continue with the normal distribution today. So let me change us to writing mode. Okay, it's not showing up. Okay, weird. There we go. God, I hate when this happens. Like sometimes it just doesn't want to do stuff. Okay. So let's talk about the normal distribution. Okay, so we've learned a variety of things about the normal distribution. It's a particular type of continuous numerical continuous distribution. And we learned that it is symmetric, it has no outliers, and you use the mean as the center because it's symmetric and the standard deviation is the spread. And these two pieces of information are called the parameters because you need them to describe your numerical distribution. So when you're talking about a numerical distribution, remember use the symbol mu, which is that funny looking mu, U looking thing with the sigma, right? Mu means the mean, the sigma means the standard deviation. And I gave you some examples of like what these graphs would look like. Like here's a normal distribution with a mean of 5 and a standard deviation of 1, and a normal distribution with a mean of 20 and a standard deviation of 5. So you can see that when you look at the normal distribution with the larger spread, the graph is more spread out and it's shorter. If you look at the distribution with the smaller spread, you can see that the graph is taller, it's more compact around the mean, and it's not as wide. Okay. And so then we had a bit of a discussion about like normal distributions, like where do they show up? And we talked about the fact that standardized test scores follow a normal distribution, and that you can actually, the whole point of using normal distributions or standardized distributions is that it allows you to make comparisons between the different distributions. So like we talked about how the SAT, that's normally distributed, the typical score is 1100, and then the ACT, another standardized test, has a typical score of 21. So we were wondering like, oh, if you get like, what did the example say? If you get like a 1300 on the SAT or a 24 on the ACT, you're wondering which one is better. Like, because you can't just compare the numbers. You can't just say, oh, 1300 is bigger than 24. That would make no sense. So you need to put them both into a place where you can make a common comparison between them. And we learned about z-scores. Z-scores are used for doing this. So z-scores take things from two distributions and put them into something called the standard normal distribution, and you make your comparison there. Okay, and we talked about how to calculate it. You do the value minus the mean divided by the standard deviation. So it gives you some number, and you do the comparison there. So we went over some examples of how to compute them and talked about comparing them. And then last time we finished with the empirical rule. So what do we remember about the empirical rule? Like, what are the things that the empirical rule tells you? Let's see if people remember. See if people are here listening, or is it just me speaking to the little gray boxes, shouting into the void? So what do we remember about the empirical distribution? So, okay, yeah, it tells you about percentage and number of standard deviations. Let's go a little more detail. Yes, that's another name for it. So, like, what does the 68% mean? Like, what do we know about it? So, like, 68% of what? Okay, so 68% of the population will be within one standard deviation from the mean, yes. So, like, for this, so, like, if we look at this example right here with the heights, right, for males. Okay, wait. Exactly, right. So like if you look here, the mean is at 5'8", the standard deviation is 2 inches, so if you go one standard deviation in each direction, that'll be 5'6" to 5'10", right? Because you do 5'8" plus 2 inches is 5'10". 5'8", minus 2 inches is going to be 5'6". So you have that range there you're dealing with. That's 68% of men. Okay, and you can keep doing that, exactly. So we learned about that. We went and did a bunch of examples. This is a good question. Why do we only go up to 3 standard deviations? Like, why not go up to 4 or 5? Right, yeah, 3 standard deviations is 99.7. Like, there's really no point in going out any further because you only have like 0.3% left over, right? Like, you don't get much extra information when you do that. So you always remember that. Basically, the 3 standard deviations is almost everyone. Okay. So what we're going to do today is, let me write an example. Shit, where'd my thing go? Sorry, I didn't plug in my writing pad. Okay, is this working? No, it's not. There we go, now it is. Okay, so let's come up with a... Oh man, I know. Okay. Okay, cool. So, what's the typical length of a pregnancy? A human pregnancy? Yeah, so we think of a typical human pregnancy as lasting 9 months. Oops, 9 months. Now, how many days are there in a month? Approximately? Yep. Which means we can do 9 times 30, which will be the number of days. And 9 times 30 is 270 days. But interesting fact, the lengths or duration of human pregnancies follow a normal distribution. So they are normally... Oh, burrito. Stop. They're normally distributed. Shh. Stop. They're normally distributed. And the average is actually not 270 days. It's 266 days. And the standard deviation for pregnancies is 14 days. And 14 days in terms of months is approximately what? Yeah, so that's 2 weeks, good, yeah. So the standard deviation is 2 weeks. And 266 days is a little less than 9 months. It's basically like 8.7 months. We just round up, basically. Okay, so let's draw our distribution curve. So let's draw the little normal distribution curve. Draw the line. Draw the ghost. So here's 266 days, which is about 8.7 months. Now if you go 1 standard deviation in each direction, you end up like right there. So you do 266 plus 14, which will be 280. And 2 weeks is basically like half a month. So if you started off at 8.7 months, that will put you at 9.2 months. And if you do 266 minus 14, you get 262, 252. which is like 8.2 months. Okay, so what do we know about the pregnancies that last between 8.2 and 9.2 months? Well, yeah, but I meant by in terms of the empirical role. We'll get to that later. Yeah, the pregnancies that last between 8.2 and 9.2 months are 68% of pregnancies. Can someone go look up for me, like, what is the definition of a premature birth? Like, how many weeks or days along is that? So someone Google that, please. What is the definition of a premature birth? Okay, so a preemie is born before the 37th week. 37 times 7 equals 259. Really? That's 259 days? 37th week? Huh. Okay, let me Google this for a second. 1 second. A preterm birth is birth before the 37th week of pregnancy. Regular pregnancies usually last 40 weeks. And 40 times 7 is 280 days. Preemies indicate. So, this makes no sense. I feel like the average should be 280 then. Okay, I need to do some more internet sleuthing. Because I think our numbers are fucked up here. This doesn't seem right. I think my numbers are wrong. Because if it's 264... Okay, I found some articles. I want my what I'm talking about to be accurate. I was too trusting with the first numbers that I came across. If you look at the duration of human pregnancy, introduction, the duration of human pregnancy is arbitrarily taken as 280 days. Results, among 1,000 women, the mean gestational age was 272 days. Oh, okay, there we go. Okay, so we're going to change our numbers. Apparently, newer research says that the average is not 266, but 272. And the standard deviation is 9 days. Okay, let's erase those numbers. Okay, so let's start off here at 272. So if you add 9, you're going to get 281. If you subtract 9, you're going to get 263. Okay, cool. I Googled and I found this article from the National Institutes of Health from 2006, and the title is about looking at the duration of human pregnancy, and here is the results section. So it was a study of 1,094 women, and they noticed basically that the average length of pregnancy was 272 days. This whole article is about how like we usually arbitrarily take the length of a pregnancy as normal as 280, but apparently the data actually shows that average pregnancies, typical pregnancies, are 272 days long. Why was I looking at this? Because I wanted to look at the definition of preemie. I feel like there's different definitions of preemie, but whatever. So we'll just roll with the one we've got. Okay, so we've got 1 standard deviation. Okay, let's go 2 standard deviations. So if you keep going to the left and to the right. So you take 281, you add 9, you're going to get 290 days. If you take 263 and you subtract 9, you're going to get 254 days. Okay, then we can go one more for that 3 standard deviations. So 254 minus 9 is 245. 290 plus 9 is 299. So we have our numbers. So from what we learned, we don't really care about going past the 3rd standard deviation because what percentage in total is going to be out there past the 3 standard deviations? Yeah, the 0.3%. So you get like 0.15% over here, and you get 0.15% over here. And this actually gets really interesting because like, how many weeks are there in a year? Actually, well, here, let's say 10 months. Each month has like, so what's the definition of a month? A month is like a certain number of days. So if you look at 10 months, that's 10 times 30 days. That's 300 days, right? Does everyone agree that 10 months is basically about 300 days? Where is the cutoff, basically, for how long a pregnancy will be, according to our graph here? It's like, what's the longest pregnancy that we really expect to happen for the most part? Right, which is 1 day off, right? This is basically 10 months. So what percentage of women have pregnancies longer than 10 months? Not 0.3, 0.15, because they're the half of it. Right, because there's 0.15 on the right and 0.15 on the left. So 0.15% of women have pregnancies longer than 10 months. This is sad. For anyone who's been pregnant, if like once you get to that like last month, it's pretty shitty. So can you imagine having to go one more month like that? That happens to 0.15% of women approximately. So 0.15% of women have pregnancies longer than 10 months. Sad. Okay. So, we can figure out all sorts of stuff here. Like, we can figure out, like, percentage of pregnancies between 263 and 281. Why? Because that's 1 standard deviation. We can figure out, like, the length of the percentage of pregnancies that's between 254 days and 290 days, because that's 2 standard deviations. We can figure out the percentage of pregnancies between 245 and 299 days, because that's 3 standard deviations. But, okay, what the hell? Why is it not letting me click on stuff? Okay, there we go. What if you want to figure out the percentage of pregnancies lasting between, I don't know, I'm just going to make some numbers up here, 250 days and 295 days. Could you use the empirical rule to figure this out? No, because the empirical rule requires that the numbers that you're dealing with are a whole number of standard deviations away from your mean. Now, if you move in terms of standard deviations, the numbers you get are 263, 254, 245, 281, 290, and 299. These two numbers aren't in that list. Okay, so that's what we're going to talk about today. Like, what about if you need to figure out like the proportion of pregnancies and like the numbers you're saying, oh, between here and here or something like that, and the numbers don't fall on that list of numbers that we came up with. So what do you do then? So what you're going to have to do is use Wolfram. Yeah, but it's really shitty. There's this thing called the probability tables, and they're like sort of a pain to use, and they're not as accurate. So I highly recommend you learn to use Wolfram. Because I'm going to open up a Wolfram. Burrito, be quiet. Shh. It's a monster. He's harassing people. Burrito's a harasser. Now he's like laying down. He's like a couple feet away from me. He's on his little dog bed. Sort of funny. Okay. Yeah, I know, trying to stay all innocent. He's like curled up, laying down. He just like randomly lifts his head and starts barking, and then just like goes back to sleep. It like makes no sense. So, I guess I want to talk about something here. So, what percentage of pregnancies last between 8.2 and 9.2 months? So what percentage of them? Like if a woman is getting pregnant, if a bunch of women get pregnant, what percentage of them are going to have pregnancies between 8.2 and 9.2 months? According to this, stop. According to this, 68% of all women. So you can actually rewrite this as a probability. You can basically say the probability of having a pregnancy between, let's just do the number of days, 263 and 281 days is 68%. Okay, so whenever we make these statements like, oh, 68% of pregnancies are like this long, you can basically think of it, what you're saying is like, well, that's the probability that your pregnancy will be that long. Okay, so the command to calculate probabilities in Wolfram is called probability. Let me write that nicer. So the command to calculate probabilities is probability. Okay, then you're going to have to put stuff inside of there to tell Wolfram what you're doing. So notice my brackets. Okay. So what you're going to do is you're going to have a name of a variable, and you're going to put it in there what you want to know about that variable. So for instance, we can say that the length of a pregnancy is between 263 and 281 days. So does everyone see how I wrote here 263 less than preg less than or equal to 281? Does it make sense that preg is the name of my variable, which is about the length of the pregnancy? You can put whatever you want there. Okay. Now, what do we know about the pregnancy variable? What sort of distribution is it? Like, pregnancies follow what sort of distribution? Yes. So the way that you do, what you have to put in next after you put a comma is you have to tell Wolfram, hey, the variable preg is distributed. So this little symbol right here, it looks like two little lines, is the distributed symbol. So preg is distributed according to a normal distribution. So you have to go and tell Wolfram, hey, I'm dealing with a normal distribution. And what are the two numbers that you always have to give? What are the two numbers or parameters that you always have to give when you're dealing with a normal distribution? What are the two pieces of information you have to provide? Yeah, in this case, our mean is 272 and our standard deviation is 9. So that's your mean. That's your standard deviation. And Wolfram in this case will spit out the number 0.68. Why? Because there's a 68% chance that a pregnancy is between 263 and 281 days if pregnancies are normally distributed. So we're going to go to Wolfram in a minute and work with this. How many people here have Apple phones? Three. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cool. Can everyone go to screen time? You know how there's screen time? Yeah, this is gonna be awesome. Okay, I'm gonna change it so that we're looking at Wolfram right now. Crap, where'd it go? Okay, 1 second. Okay, cool. There. So I'm gonna have a variable called daily average. Okay, my daily average on my phone / devices apparently is 10.5 hours. Drop them in the chat. Your screen times. That's because I'm on my phone or teaching all day long, and it counts the screen time from all devices from this, because, I'm here. Don't judge me! Okay, so throw some numbers in there. 4, 5.4, 2.7, 6, 5.5, 2, 3.5, 5.9, 6.2, 4, 5.75, 4. Okay, any others? And then I'll put a 6. Yeah, I know. I spend a lot of time on my devices. Well, I spend a lot of time in front of the computer. Daily average, yeah. Yes, it is. Okay, another 6. Okay, any others? Oh, I missed the earlier ones. I missed the first 4. I missed the first... Actually, no, I got it. I did. Okay, 6.5. Nice. Okay. So, let's calculate what the mean is of our daily average. Okay, 4.9, and what's the standard deviation of our daily average? Okay, Okay, cool. So according to this is why the phones go by faster. Yeah, I know. The years go faster always on our phones. So according to this, the daily average for us as a group is 5 with a standard deviation of about 2. Okay, cool. So we can start asking ourselves questions such as, what is the probability that someone spends more than 6 hours a day on average on their phone, according to this? So we use the probability command. Okay, what should we use as the variable for the amount of time that the person spends on the phone? Like, what should we call this variable? It doesn't matter what you call it, you just need to choose a name. I like that time. So we want to know the probability that time is more than 6 hours per day. So what do I have to say? Time is what compared to 6? What needs to go between them? Yep, exactly. So I want to know the probability that time is greater than 6. Now you have to tell Wolfram what sort of distribution time follows. Now, time follows a normal distribution. So the way you put that little distributed symbol to tell you that that's what the distribution is you're going to put a backslash, bracket, distributed. And it just turns into it automatically. So backslash, bracket, distributed, like this, will end up becoming that thing. So I type backslash, bracket, distributed. It becomes zit. Oops, I did not put it in the right place. Distributed. Distributed. Okay. Now you have to tell it that it's a normal distribution. So you type in normal distribution. Okay, then I have to give it 2 numbers. What was my mean? What was the average or typical amount of time spent per day on the phone? 5. What was the standard deviation? 2. We're just rounding. And now you run it. Okay. I would tell you specifically for the question. So for here, I'm just going to say that we're rounding to the nearest... let's round to the nearest decimal, 10th. So I guess we'll round that to 2.2. How does that sound? Yeah, it will be specified, yes. And then look what we get here. When we round it... So what is the chance that someone spends more than 6 hours a day on their phone, according to the data we have? There is a 32% probability that a person in this class spends more than 6 hours per day on their phone / devices. Boom. Well, let's look. That's a good question. Because, yeah, you should look at that. So we'll do daily average histogram. Oh, it's actually pretty close. Yeah. Like, obviously, this looks like an outlier and there's sort of a gap right there. But, like, you can see, like, does everyone see how it goes if you, like, were to draw, like, a little line over it? It goes up and then down. Yeah, I know, that was me. That was me. If you throw me out, let's see what happens. So if you get rid of 10.5 and rerun, the average is 4.5 and the standard deviation is 1.6. So actually, let's rerun it. So excluding me, the average is 4.5 and the standard deviation is 1.6. And it becomes a 17% chance. And let's look at the histogram without me. The histogram without me looks like this. Sort of symmetric, but not so much. But it looks sort of normal. Okay. So, we're going to do some more problems like this. I'll show you like how you can do some calculations. And there's actually all sorts of cool stuff. So, let's go to Google and find some. Oh yeah. Let's use men's heights. Oh yeah. The distributed. Right here. Type that in \bracket distributed end bracket. It will automatically make it for you after you press the space. No problem. Okay, so we'll do one together. So plain text. We know that the heights of US adult males are normally distributed. And we know that their distribution is a normal distribution with the average height is 70 inches and a standard deviation of 3.3 inches. So with a mean height of 70 inches, so let's actually, Wolfram can do some cool stuff here. Let's do 70 inches to feet. Cool. Okay, not cool. I want that as a number. 5.8 feet tall. Okay, cool. So, average, according to the information I'm looking at here, average height is 70 inches for US adult males. Standard deviation is 3.3 inches. Oh, scroll. Yeah. Cool. Okay, so let's say that we know that the heights of US adult males are normally distributed with a mean height of 70 inches and a standard deviation of 3.3 inches. So let's say that you want to do some calculations now. You want to know what is the probability that a man is taller than 6'4". So first of all, you have to convert that to inches, and like Wolfram will do all sorts of cool stuff for you. So like what I like to do is when I go to the plus, I go to the Wolfram alpha query or the freeform input. So you can do like 6'4" 2 inches. Apparently that's 76 inches. Okay, so we want to know what's the probability that some guy is taller than 76 inches. So we can set this up. We can say probability. Okay, so because we're talking about how tall someone is, why don't we use the variable height? So we want to know the probability that someone's height is greater than 76 inches. You put a comma. Now you have to tell Wolfram how the distribution that height follows. So you do height, you do your bracket, so your backslash, your bracket, you say distributed, boom. You tell it, hey, this is a normal distribution. You give it the mean. The mean was 70 inches. The standard deviation was 3.3. You run the problem. And then what do you find out? What percentage of men are taller than 6'4" approximately? So looking at this, what percentage of men are taller than 6'4" in America if the average height is 70 inches with a standard deviation of 3.3 inches? So looking at that number, what is that as a percentage? What is 0.03 as a percentage? Yeah. Okay. Only 3.4% of men are going to be taller than 6'4". Does anyone know what the average height is in the NBA? Can someone Google that for us? What's the height of an average NBA player? Let's see if Wolfram can tell us. So I'm going to go. Yeah, actually we do. We could go in there and look it up, but it's easier if we just ask average height NBA player. See if we can find it. Okay, you have to do Wolfram Alpha Query. Oh, you press that little plus button and you choose Wolfram input. Oh, here. Oh shit, nice. Yeah, actually it is. It apparently just took a minute for it to figure it out. So apparently the median height is what? 6'6". Yeah, I know, this is pretty cool. Apparently the tallest NBA player ever was 7'3", 7'7", and oh shit, shortest ever, 5'3". Now here's the crazy thing: the median is basically typical, average, right? So if you look at an average NBA player, that's like taller than 6'4", right? And what percentage of men are even going to be 6'4" in the first place? 3.4%. So like the average NBA player is in that like top 3.4% of men by height. Like you can actually get like an idea of like how freakishly big those people are. Let's actually do this. So the median is 6'6". Let's redo this. Let's do 6'6" to inches. 6'6" to inches is 78 inches. So let's go and put 78 here. What percentage of men are taller than 6'6"? Oh my god. What is it? What percentage of men are taller than 6'6"? So what is that decimal there as a percentage? Yeah, so we'll just do that as 0.8. We'll round it. Okay. That's normal in the NBA, right? 6'6". But if you look at all men, that's in the top 1%. The NBA players are the top 1% of height. They're hoarding the rest of the height from us. That's like what's going on, basically. Like, it sort of shows you how, like, skewed looking at those players is. Like, they are in the top 1% in terms of height. But, like, they're normal in, like, or typical in that arena. So it's sort of crazy when you start thinking about stuff this way. What's something else we can look at, like other than height of NBA players? Age? Age, unfortunately, is usually not normally distributed. Oh, hand size? Holy shit, sure, why not? Yeah. Oh, or how about this? Let's do NFL players. And what should we look at on them? Whoa, look at all this. Dang, nuts. Yeah. You knew where I'm going. Let's look at how big these boys are. So, average weight NFL players. Let's see what it tells us. It apparently takes a minute for it to think about it. Some cool stuff. Okay, it's thinking. Unfortunately, that's not a number. Otherwise, yeah, we would look at stuff like that. We could look at maybe like percentage of different races in the NFL versus like population. But let's look at weight because we all know that they're going to be huge. Okay, why is this like not coming through? Oh, because it's not... Crap, it's not a... I clicked the wrong type of command. Freeform input. Average weight NFL player. Come on. What? No interpretations available. Okay, this is bullshit. What the hell? I'm sad. Why is it not working? Okay, let's try something else. Let's do... let's not do Wingspan. I want something cool. Yeah. Average shoe size US male. See if it has anything for us. Okay, I don't understand, like, it worked once. Why is it, like, not working again? No interpretations available. How about average shoe size NBA player? No interpretations available. Oh, wait. Oh, shoe size. Okay, this is gonna work. No, that's not good. Okay, something else. Yeah, I guess that's right. Okay, I'm gonna go and just find the average weight of NFL players. Average weight NFL players. Apparently someone did a stats project about this. Okay, cool. I'm looking for the results. Okay, I've got 254 pounds. Holy shit. No, 245 pounds. Okay, so apparently let's type this down. So, the average NFL player weighs 245 pounds, approximately. Now let's look up the heights for average American males, average weight, U.S. adult male. And what's the median standard deviation? Okay, I'm looking. Okay, cool. The The mean weight for U.S. adult males is, drumroll, 172 pounds. With a standard deviation of... I just lost it. Where did my tab go? 29 pounds. So let's figure out, like, what is the probability someone weighs at least someone weighs at least the NFL average. So you can go here and you get like probability. Okay, let's use weight. So you want to know that the fact that their weight being more than 245, and then weight is going to be distributed according to a normal distribution, where the average is, the mean is 172 and the standard deviation is 29. Okay, whenever it gives you this weird number, like a thing like that, just put / uppercase N to give yourselves a decimal. And it's like, oh shoot, what is the chance that a US adult male weighs at least the average for the NFL? Oh my god, that's 0.6%. So this is sort of crazy. If you look at the men in the NFL, and if you look at their weight, they're being average there puts you in the top 0.6% of all males. So they are rather large, basically, if you're just looking at their weights. So here's my question. Does it make sense how you use the commands to figure this out? That's what I want to know at this point. Any questions about typing in the command? Does everyone want to try and go give it a go on Wolfram? So I can see if you need any help. Everyone open up a Wolfram thing. Try to do it. I don't know, I might be speaking into the void right now. I never know. Is anybody out there? Is anybody out there? Good. No. Nice. That was hilarious. Oh, hey, it's you. We haven't seen you forever. You having a good time doing statistics with us? Oh, hey. Good times. So I want to give you an opportunity just to see that you can type in the commands and run them, because sometimes, like, learning this, like, you're like, oh yeah, of course. So take a moment. Let's see if you can do it. If you get stuck somewhere, I will look at your screen. Yeah, try running this one. Just make sure that you can type it in properly. Especially getting that distributed thing right there. Sometimes people have difficulties. I just want to make sure that everyone can do it. Yeah. Yeah. It makes no difference if you put greater than or equal to. Mm-hmm. At least for this. In other cases, things that we deal with eventually, it will make a difference. But for this one, no. Oh, yeah. So for now, it makes no difference when you calculate it for the normal distribution, but for these other distributions we're going to deal with, yeah, it will make a difference. So just to let you know, at least would normally be a greater than or equal to, because like it would include it or more. Mm-hmm. No problem. Oh yeah, sure. Let's go down. There you go. So backslash, bracket, distributed, bracket. And then if you press space after you type it, it should turn it into it automatically. Oh, you're talking about right here? So you do backslash, open bracket, distributed, close bracket, and then if you press a spacebar afterwards, it should like magically change. So like, let me like show you. If you look at me, backslash, bracket, distributed, and then when you do the closing bracket, it should turn. My internet has been acting up recently. Has anyone else been having internet issues? Out of curiosity. I like how everyone just like is like yes at the same time. I've like been wondering like what like I haven't had any internet issues until today. Like, is this a common thing for you guys, or are you also just having it today? Huh, that's interesting. Yeah, because I started having problems last night, basically. It was fine until last night, I'd say. Oh, yeah, I have Xfinity here. Do people? Oh, my phone is getting internet just fine, like really fast. I wonder if it's Xfinity. How do you do the orange thing? Oh, so what you do is you like put the little mouse and there's like a little plus that shows up on the left, and then you'll see a thing that says freeform input. So yeah, so I've been wondering about it. Like, is it something with Xfinity? Like, must be like the Chinese like cyber terrorizing us. No offense to people who are, ethnically so. Just facts. That is a thing. Does anyone know about that? Like, there's like all sorts of hacking that countries are doing. Like they like take down power stations. They do all sorts of shit. Yeah, you can show your screen. So you're trying to okay. So you have to do backward slash. That's a forward slash. Okay, open bracket. Nope, that's an open brace. There we go. Now distributed. Now do you see that? Keep typing distrib-t. There you go. And if you just click on that, it will finish it for you. There. Don't remember when you left. No, I'm making sure that you can type in this command to calculate a probability. So let's do that. We're doing that. We're making sure that like you can type this in and get the distributed symbol and calculate this number. No, I just need to make sure that you can do this. So just chill out until I've confirmed if everyone can do it or not. We don't have much more time, do we? Yeah, we're like basically done. So I'm going to tell you this. When you've been able to type this command in, because you're going to need to do it to do the homework, you're good to go. Does that make sense? I'm just going to stay here until everyone has verified that they can do it. So if you're done, you're good to go. And I should just end the recording here because it's just going to be us, like, me answering questions.